I have a presentation that's 84 slides. There you are. Okay. I'm not going to go through 84 slides. It's just easier for me to just not butcher my slide deck. So introduce you to what eSEES is. Took me a while to come up with that name. I'm not so sure about it, but I wanted to sound easy. And no, the letters don't really stand for anything other than how it sounds. I think it's System for Earthquake Engineering Simulation. So it's like easy system for blah, blah, blah. But anyways, I like the sound of it and the aesthetics of it. I'm a big fan of scripts. I think the user interface for OpenSees, the scripting user interface, is the best, the most powerful, and most versatile. But it's not the most user-friendly, let's say. But I didn't want to build a graphical user interface and leave out the opportunities that you have with scripting.
The scripting is in Tcl or in Python? It's going to be or both?
So right now it's in Tcl because I think Tcl is better than Python.
No way.
But oh my gosh, don't even get me. So that's a whole other session. We can have a whole other session on that one. So I'm from the old days of Tcl. In my days, Python was not quite fashionable until the Stanford folks made it fashionable. I know Python. I do a lot of programming in Python. I just haven't, this is where I started. I started this program about 10 some years ago. And so what I'm thinking of is integrating Python commands. Tcl and Python are interchangeable. I like the TK graphic part of it, all the little menus and pull down menus. And Python actually uses TK. So that's a whole other thing. So right now it's in Tcl TK, but you could write Python code that will write the input for it. So I have to figure out now an interface for this interface. But let me show it to you because it's really just about developing a new language. And so then it's just the semantics. I mean, I can just write this command could be coming, whether it's in Python or it's in Tcl, it doesn't really matter. But right now it's in Tcl because I like Tcl and mainly because that's where this started. The point of it for me is I wanted to, one is maintain the flexibility of the scripting as well as, and there's just a long list here. What I wanted to do is, okay, here's the drawings. Here's, the actual quantities. I don't want to have to look up, since I wrote the manual for OpenSees. Well, I really just translated one. I made the first online one. It's a pain. The semantics of it are a pain. And so I really wanted to build something that was above it. And, what is that F3, 4, F pi of the pinching 4 model? That question came up the other day, and I really have no idea. And oftentimes you take default values for that. So I really wanted something that was minimal input for the user, but I didn't want to hide the input. So I'm going to show you what I actually did. This slide, I think I have everything on here. And also the ability to run OpenSees real time in integrating it as part of it. Here's just an example, for example, that I even brought units in. I don't know if you guys, I brought units into OpenSees scripts a long time ago with that little script that defines units, because units are just variables anyways. I learned that from using MathCAD. And this is really just to show you what I like about the TK interface, just the little windows and widgets that are available in TK. So that was really important. As much as you can go to Jupyter notebooks and things like that these days, I wrote a Jupyter notebook for the ground motion selection for SCEC, and it just doesn't have the sophistication that these widgets have. So I like this part of that it's associated with Tcl TK. And yes, you have to write the scripts yourself. But so here's the perfect example of my goal with writing this user interface. So eSEES is not a GUI, it's a UI. GUIs are so 90s, right? UIs are really the way to go now, where you can write a script or you can deal with the graphical user interface, and they interchange the two. And I'm going to show you a slide later, but whatever you input in the graphic component, it then saves it into what I see here. This is eSEES language. It's a whole other kind of higher level language above that language of saying, okay, add some material data where you've got a name, you've got a type, and then all I care for is 4,000 PSI. I don't know what, and it's confined to concrete. I don't know what all the other parameters that OpenSEES has. And the point of it was also that this is actually something that you can translate into a different language as well. And so just like this program writes OpenSEES code, the input file in OpenSEES, the TK version, I can just have a translator and have these data be translated into the Python, because that's just, you know, a line that I tell my program what the input file is or the input command is. But I really wanted to keep the user away from the input command and just say, okay, 4,000 PSI concrete, and then all these other little values here are optional. So the nice thing about the GUI is that you can visualize what those options are, but you don't have to touch them. So there's definitely a lot of advantages to dealing with the graphical user interface. But as you can say, I'm not defining points, and maybe, you know, the material doesn't even have F'C as the main input. It may have derived values. And so that's really what I wanted to do in what I had in mind when I kind of came up with a layer on top of the scripting layer, so that it knows what the format is in OpenSEES, but the user doesn't have to know about it. It's what I like about, and so there's this is just a quick little outline, and what I can do is I can publish this presentation so people can actually get a little bit more details into it. The scripting, as I said, it's wonderful because you can take advantage, whether it's Python or Tickle. You don't want to lose having a programmable user input. And then the graphical user interface is handy because you can visualize your input and you can run OpenSEES real time. Here's an example, for example, of a for each statement in Tickle. So here's kind of the format. It's got menus. I think it's kind of cool. But what's really nice is the user interface for looking at materials. And it can actually help you to build an element or a material and really test out what is the effect of the different parameters. It's broken down, as I was saying before, into required arguments and then optional arguments. So you see, I've put in 57 root F prime C for the E sub C, which then for concrete 2, you actually have to compute something else. And so this kind of does all those input parameters for you. It's just a list of features. What's nice is the model input is defined as you define elevations, and then you define a grid, and then you take those elevations and you place them on the grid. And so this is how you define a 3D frame. There are no nodes of no number one, you know, these are the local coordinates. Of course, right now it's based on Cartesian coordinates, so you have to have some sort of regularity. But you see, you define a geometry, you know, the floor heights, bay widths, and it could be different for different bays. And then in the background, I go in and I compute the node numbers. And then I go in and generate an OpenSEES input file. And so I go through this process for materials. And I think I have most of popular materials. I've laid things out where I can just add another material if I want. I've got some templates for fiber sections. So it's really cool because you can, in real time, give the size of the rebar and the number, and you can test your moment curvature. So I've got templates for those. Here's an example of, so for example, you've got minimal input where you just pull out, you know, pull down what are the materials that you have. And then there's additional default parameters as well to just make it that much more interesting. So you can really look at, you know, different behaviors and different cross sections, and you can really have a lot of fun with it. So it's nice because you can compute, you can do some moment curvature analysis. You could just this program just for that if you want to. And then just as you have it in graphics, well, here's how that input would be. So I've shown you a material. This is how it would be for a cross section in reinforced concrete section. Or even do the same thing even for element types. And so I'm going to just kind of fly through here. Oh, and then, oh, good, I did fly through those parts. Then there's the building the 3D model. So here's how you use the interface to define your elevations. And as you can see, there's nice click on or, you know, quick menus. There's a lot more menus now than when I had then. Or you can write that in a script. if you do it graphically, it's going to write it to a script. If you do the script, it's going to load it up graphically. There's lots of different types of elements you can interactively change, and this is just to kind of walk you through all the little menu options that you have. A lot of these things have changed as well. And what's really cool is gravity loads. You can define gravity loads, and then I convert those into loads and masses directly. You don't have to do it. Or you can do nodal masses and nodal forces that are just uncoupled if you want to. So, you know, it does that whole computing of the mass for you. It also computes, you know, the equivalent mass at the nodes. So it's just an interface that, and I'm just literally, it's kind of cool because then you just click on, you pick an elevation and you click it on the grid and it appears on the right-hand side. So there's a lot of programming that went on behind it to really minimize how much work you as a user need to do. The less of a human interface there is or interaction there, the more repeatable and less likely we are to, you know, make mistakes, but also just speeds up. Oh, what if I have variations on this? You know, it's kind of fun to be able to visualize this frame here is actually defined using these scripts. And then there's a whole, you know, a lot more features. And then even in the post-processing, it's kind of cool to visualize. Oh, then it's got loads and load combinations that are defined. And then this, you can actually run the OpenSees real time. And if you want, you can visualize, you've seen these scripts, they're in the examples manual. I implemented them to be able to visualize the analyses in real time. And then you can visualize the results, typical things of results, the color of the element, and look at the node responses. And actually, it's kind of cool. You can visualize bending moment diagrams, cross sections, and then only select certain things. Oh, look at that. I wanted to show you, oh, you can look at the history, but then you can actually get all the way to the fibers, what the fiber stress strain history is. And this one's a little tricky because this is actually not done. So the problem that I have is you don't want to have all these recorders during the analysis. But I've gone in and spent the time on it. It's like, wait a minute, if I have certain output, I can recreate this. And so you can go down to your stresses and strains without having to store those during the analysis. So that makes the analysis a lot faster and you don't have to store so much data. And so that's pretty much, I think it's wonderful. I think everybody should be using it, but I wanted to kind of show you a different way of approaching a user interface where it's not just graphics and just looking at your model, but really kind of redefining, it's almost more of a BIM type of system. So that's the little dog and pony show. Any questions on that before I switch back to more starting really a conversation where I have bullet items with you guys? Yeah.
How are you solving the convergence issues when you're making complex models? Because they do have, when you're using certain materials, certain combinations. For example, in a commercial software, you most of the time you don't have any issue and it will give you a result. And how is it with this one?
So it's twofold. Yeah, the commercial programs hide it and they put in a lot of numerical damping so that you don't have convergence issues. So what I have done is it's the script, the classical script of convergence. And I wish, I thought I had it here. Let me show you. Just a classic script of, if it doesn't converge, take this step, and it does just the usual algorithm that I developed with Frank that's in the examples manual. That's going to work 90% of the time. If your model has convergence problem, 97.5% of the time, you should go back and check your model.
Yeah.
Okay. And so if it can't get past my script, there's something not very likely. It's really with your model. And that's kind of the point of eSEES also. It was like, go back and check, and everybody was fine. Well, if your cross section is made of pure concrete, it's not going to go very far. You are going to have problems. It's telling you, hey, there's some, if the response in your cross section is impacting the overall convergence of your system and you don't have load redistribution, then you really need to go back and look at your model and look at your sections, or really look at your buildings, and those convergence issues are there. Now, the second part is this actually generates an OpenSees input file. And so if I could find it, there it is. There's my demo. So, I may not have saved it. Yeah, there it is. So if you want, here's, every time I run an analysis, it gives you the tickle file. And so this is the input, but let's look at the output. So this example here actually had a whole bunch of convergence issues, but the script actually helped it. And oh no, you see, it didn't converge. But honestly, because this was just a crappy model that I just put together to do a little demo. Okay. And so it was bound to not to converge, because I don't think the structure should have been standing with the gravity loads that I gave it. But if you want, now you can say, okay, well, let me go back. If it's a really problematic problem, then here's your script. That's cool. Here's your OpenSees input file. It's kind of cool because you can learn a lot from these input files as well. And so somewhere here, see, it's a big model. So you can go in if you want to and improve this convergence here and see if you can improve it. Okay. And then if you want, one is you can send it to me and say, hey, I found something that really helps it. Because if you run this file on your own, I won't post-process. I need to figure out a way. I want to put it that now maybe as a user, you could put in little scripts. And so if people run into this and that's a problem, I'm happy to, I'd love to improve this program. And like your question now is like making me think, oh, I should have a user-defined script, to help with convergence. But again, you can go in and look at this and put in the scripts that you want and modify it. At least it has helped you to generate an OpenSees input file. And so if you have something really complicated, it's a great place to start. Now you can add things to it, and you can even use it this way to really just build your overall frame. And then now you can take it and run with it. You've got an OpenSees input file that you can do things with. You know what I mean? So that's the way I handle it at this point. It's not a black box what it has. But again, I think it's going to help you out a lot because you can visualize your sections and predict ahead of time, and minimize situations where you forgot to put rebar or you defined a cross section with negative fibers when you meant to be positive. Sometimes it could be negative on purpose, and that's okay.